n minus I basically means that LG, so when we are at I is equal to 1, we're going to multiply that 2 to the 0 by LGN minus 1. What's LGN in the case of a full tree of 15 nodes? Well, it's roughly speaking 4 minus 1 is 3. So that gives us the basic LGN minus I will give us the maximum number of comparisons on a swap down from that level. So we're adding those things up. So that gives us, so everybody understands the model? So now we just do the summation out, so we expand it. We multiply 2i minus 1 by each of those terms in the parentheses. And that gives me two equations, two summations rather. The first summation is 2i minus 1 LGN, which is on the second row here. My pointer is weak. I can't point very well. Second row, I have this first summation minus the second summation. So continuing on the first summation, notice that LGN is a constant. So LGN comes out of the first summation, and all we're doing is adding 2 to the I minus 1 from 1 to LGN. That is a geometric series, where the first term is equal to 1, and the last term is equal to 2 to the LGN minus 1. So we can use those values to compute a geometric series. And the next one, we have summation from 1 to LGN of 2 to the I minus 1 times I. That is very similar to a series we've done before. Okay? So that also can be solved relatively easily. So this geometric series, the first geometric series, this one right here, gets solved right here. And then this one is going to be solved right in here. And there's a few ways of solving it. So I'm solving it right here. Okay? And so what we have is we have n LGN on the bottom minus LGN minus the summation. And that circles that summation. So the solution is going to be this one. So it's going to be n, or simplified. So, or is that the whole thing? I guess that's just a summation. So now we're going to take it away. That's fine. So we're going to have n LGN on the second line, n LGN minus LGN minus, that's a circle. So the result is, when we simplify this stuff, we're going to get n minus LGN minus 1. So that's a very interesting result. Why? Because it tells us what? What does this result tell us? It tells us that a heap can be constructed in linear time, which means that if I have an array of 1,000,000 elements, okay? If I have an array of 1,000,000 elements, I can construct it in a millisecond. Very fast. If I have an array of 1,000,000,000 elements, I can construct it in a second, or parts thereof. You understand what I'm saying? So building a heap is really, really cheap. Even if you have 1,000,000,000 elements, in 1 second you can have those elements constructed into a heap, so very, very fast. Okay, so let's talk about what is a heap sort, because heap sort is another type of sort, which will utilize the heap structure. Now, creating a heap does not sort your array. We know that already. If I get a max heap, the only thing I'm going to get in linear time is the maximum number. But if I get the maximum number, I know that the next maximum numbers are not far behind. They want to come up. They're high up in the tree. So, what is a heap sort? A heap sort is given an array of n elements. The algorithm of heap sort is as follows. The first thing we're going to do is turn the array into a max heap. We just saw that has a complexity of theta n. Now, what we're going to do is we're going to follow this loop for n down to 2, which is n minus 1. So we're going to do the loop roughly n times. Here's what we're going to do. What is n again? What is n representing? The number of elements in the heap. So for n down to 2, here's what we're going to do. We're going to exchange a1 with an. So think of the array now. Put your mind into a linear thinking. what is exchanging A1 with AM going to do? It's going to exchange the root with the last child. Clearly, if we have a max heap, so let's think of it as a tree, if you will. Here's my maximum value. Here's my bottom level. It's a full tree. So so this is basically the rightmost child at the bottom level. I'm going to exchange them. Okay. Now let's see what that means. It means that the child coming from this deep level is going to construct a violation of the heap. But from a linear standpoint, it means that the maximum element, which was here, which is the root, is now in the last position, which is perfect for sorting. Because we want the maximum element to be in the last position of the array. So what we're going to do is we're going to exchange the root with the nth element, and then we're going to change the size of the heap from n to n minus 1. We're going to cut this element off from the heap. Which means, if we cut this element off from the heap, it doesn't cause any violation. The only violation we have right now is the root in the tree is here, or if you want to think about it here. And remember how this is going to move. We're going to be now swapped. So we have, from the tree standpoint, after we do this exchange and cut off this child, there are no violations in the subheap of the root. And there are no violations in the left subheap of the root. Only the root is in violation. So the root will be exchanged with one of its children, and then one of its children's children, and children's children. And so 1 will be exchanged with, let's say we go with the left child. Position 2, position 4, position 8, position 16, 32, 64, 128, 56, 512. We're going to be exchanging it, but we're exchanging by exponentially growing our exchange jump. And of course, that's very impressive for trees, for arrays, but for trees it's just normal behavior. But we are using a tree discipline within an array, because we know that all the nodes we want, when n is equal to the number of nodes in the tree, it works perfectly fine. So that's what we're going to do. So what's going to happen is, after we exchange this root with the nth element, which gives us the maximum going here and some small number going up here, all we have to do is swap this thing down someplace until it settles. It's probably going to go down pretty low. Why? Because it came from the bottom level. Is it going to go to the bottom level? I don't know. We'll talk about that. Probabilities, probability-wise. But once we remove this last element from the heap, and the heap becomes n minus 1, then all we have to do is swap this thing down where it belongs. And after we do that, notice the complexity of that is LGN. Or if you want, LG of n minus 1, because the heap has decreased in size. So therefore now, after we do the swap down, guess what's happening? In the first position of the array, we have the second largest element overall, which we're going to swap with index n minus 1. And now we have the last two elements are sorted. And from the n minus 1 position, we go back into the root and swap it down exponentially, which is with LGN complexity. So what are we doing? We are doing an exchange, which is theta 1. For our sort, we have a heap. We do an exchange, which is theta 1. And then we swap down. The swapping of the root into its new position after the exchange, swapping of the root position into its proper location is theta log n. Theta log n, that's what it is. How many times do we have to do it? To finish the sort. How many times do we have to exchange the root with the maximum index heap position and then swap down? Well, each time we exchange, we put one element into the sorting result. Yes? Each time we do that, we put the element into the final. So how many times can we put the correct element into the sorting result? N times. So therefore, we're going to do this swap down after the exchange N times, which has the behavior of big O of N log N. And I say big O and not big theta because I'm not sure if it's actually theta. Because when I do my first exchange, the heap has how many elements in it? N. But the next time I do it, how much does the heap have in it? N minus 1, N minus 2. So the heap is actually decreasing. So by the time I decrease it, it's very small. It almost is silly to think of this as an N complexity because the heap is getting smaller. But we're going to say big O, because we know it's no less than that. It could be, big O because we know it could be less than that. But if the heap was the same size each time, it would be N log N. By the way, that is worst case analysis, right? That's worst case analysis. Why? Because my model assumed that if I have, for example, 1,023 nodes, which has a height of 9, I'm assuming that on an exchange, that root's got to go all the way down. And it may well have to go all the way down, but it's possible it stops earlier. It's possible that many nodes stop earlier. Nobody can go more than the worst, but that was worst case analysis. That's why we have to use big O, because we just don't know. We don't know exactly. We don't know exactly. So what is the complexity of heap sort? We sort of alluded to it. Well, the analysis that I'm presenting here is a worst case analysis. The worst case analysis means multiply for each height, as height varies from 1 to h, the maximum number of swap downs at height equal to I times the number of nodes at height is equal to I. That makes sense? So that is the heap sort. So notice that if I am at height is equal to I, let's say I is equal to 1. What is height is equal to 1? How many nodes are at height is equal to 1? What is height is equal to 1 anyway? Okay, let's try h. 2 to the h minus 1. Notice that that second parameter is growing. How is that second parameter growing? It's growing exponentially, right? As I is going from 1 to k, 2 to the I minus 1 is doubling each time. Well, what's doubling each time? What doubles each time in this tree? Number of nodes. Number of nodes. So that means at the maximum value, I don't know, I'm using k here and h there. I don't know if that's kind of confusing to me too. So if I'm going from 1 to h, forget about the k, 1 to h, then 2 to the h minus 1 is the number of nodes where? For which level? What is the h value here of this tree? 4, it's 4. Yeah. So what is 2 to the third power? 8. So that's the number of nodes at the bottom level. Okay, so when I is equal to h, 2 to the h minus 1 is the number of nodes at the leaf level. Again, we're assuming a full tree for simplicity. Okay, and so now, so when I is equal to h, what is h minus 1? So when h is equal to 4, 2 to the 4 minus 1 is 2 to the third, which is 8, and then we have h minus 1. So what I'm saying is, when a node from this position is exchanged into the root, the maximum swapping is 3. When I exchange any of the bottom nodes into the root position during the sort, so 8 times I will have a swapping which goes 3. Make sense? And then 4 times I will have swapping, it's going to go 2, and 2 times I will have swapping of 1, and 1 time I will have swapping, it goes 0. And the reason that happens is because after I put n minus 1 nodes correctly into the array position, the last one is by definition in its correct position. Because all the other ones are in their correct position, so by default I am in my correct position. And so you see here, so what kind of analysis is this? Is this a worst case analysis or is this the realistic analysis? This is the worst case analysis. This is the worst case analysis. Okay, so when we finish this analysis, all the summations, I'm not going to bore you with that, we end up with having n plus 1 times LG of n plus 1 minus 2n. So we see that the complexity of it ends up in fact being n log n. So in fact, you can see it's going to be n log n plus n log n minus 2n. So the number is actually slightly smaller. The instruction count is actually slightly smaller than n log n, but it's theta n log n. That's the worst case analysis. Okay, any questions on this so far? So to review what we've done so far, the cost of building a heap is linear. The cost of heap sort is n log n. Worst case analysis. And by the way, in case you're wondering, it's also going to end up being the average analysis. And the reason for that is because the worst case, if you look at this tree, for example, imagine this tree doesn't have, in this case, as we have 15 nodes, but imagine it has a meg minus 1 nodes, which is going to be height of 20. Half the nodes are at the bottom level. So half the nodes have that worst case complexity. And they're going to tend to go to the lowest level. And we'll talk about probabilities later, but I want you to understand why. So oftentimes with binary trees, you have average complexity, sometimes following the best case for good algorithms and the worst case for bad algorithms. But in this case, it's going to be the worst case. Okay, now what about adding an element to the heap? So let's consider the complexity of adding a new element to the heap. So first of all, let's go right here. Let's go right here. So let's say we want to add an element to the heap. How do I do it? So again, go back to thinking of it as an array. So the array right now has elements, has 15 elements. Or perhaps n is equal to 15, but the array could have 1,000,000 elements in it. You know what I'm saying? The array could have a lot of space in it, but we're only using 15 elements, which means n is equal to 15, so we know that we have no greater parent than 15 divided by 2 floor of that function, which is 7. So that's the greatest parent right there. 10 is the greatest parent. So we want to add an element. How do we add an element? Think of this as an array. What do? We have an array, and we're indexing it from 1 to 1,000,000, but n is equal to 15. How do we do it? How do we add the new element into the heap and then make it a heap still? Where does it go?
At 16.
It has to go to position 16 because it has to satisfy the tree, complete tree, which means it has to be the next element in the array after 15. It goes into position 16. And of course, as it goes into position 16, it becomes the left child of that leftmost 7. Now, I don't know what value it has, but I do know that if I have a max heap here, if that value is 6, what do I do next? I'm done. If the value is 2, I'm done. If the value is 10, then what I'm going to do is I'm going to compare it to make sure it's less than a parent. And as I compare it, it's not. So that 10 exchanges with the 7. That 10, because it's bigger than the 7 to its sibling 7, goes up and swaps with the 8. And then because the 10 is bigger than the sibling 6, swaps with the 9. The 9 goes down with the 8 is, 10 goes up, and now it's fine. So what is the worst case complexity of that insertion into the heap? What's the worst case complexity of insertion into the heap? Count the number of comparisons in the worst case. Which is LGN. So its worst case is logarithmic, because the worst case is going to go up to the root. That's the worst case. Okay. So we know that the complexity of an add is going to be log n. Let's think about another structure that you might have heard of, and that is a priority queue. How many people have heard of priority queue? Okay, so priority queue is different than a FIFO queue. FIFO queue is first in, first out. It's like when you go to a grocery store and you're the first person there, so you get served immediately, but the person behind you has to wait for you, so they're second, and then the person behind you is third, and I come in on fourth. So I have to wait for one person one, and person two, and person three. First in, first out, second in, second out, third in, third out, ith in, ith out, FIFO. But priority queue is a different kind of queue structure. A priority queue is a queue where you have priorities within the elements in the queue. So for example, let's say I have a queue. Let's just imagine the queue is empty. And then say we have first element comes in. So it goes right away for service. And we'll allow it to finish. So now we have another element comes in. It's waiting. Its priority is 3. And another one comes in. Its priority is 5. Maybe 5 is bigger, is a bit more important. So what happens is that 5 takes precedence. Because we have 5 is more than 3, so 5 is going to be next. 3 goes back. If another 5 goes in, that 5 can go in either in front of this 5 or in back of this 5, but ahead of this 3. In order to do that, we have a little bit of a problem. Because basically, imagine that we have a priority queue, and we're actually putting everybody into the same queue. If you put them into the same linear queue, and you have, for example, 100 people waiting in the queue, and all of them are priority 3. And all of them are priority 3. So now a priority 5 comes in. What do you have to do now? You have to move every single person in the queue back. Every one of them. How many? Theta n. Before you put that 5 in there, and the 5 gets served. If another 5 comes in, we have to move everybody back again. If another 5, we have to move everybody except for that 5 back again. So the insertion, in this case, could have a worst case complexity of theta n. Does that make sense? If the person comes in with lowest priority, you can always put them on the end. Because they're not going to bump anybody. But if anybody comes in with a higher priority than 1, you have to make sure there are no 1s that can be bumped. If somebody comes in with a 2 or 3, then 1s and 2s can be bumped. If somebody comes with a 5, then everybody 1, 2, 3, 4 can be bumped. So the problem is it requires restructuring the queue constantly, moving the elements into position. So a lot of people don't like to implement a priority queue in this way because it is very costly. The removal process is very cheap. Theta 1. Take the first one. Okay. So the expensive one is NQ into the priority queue. Put it into the priority queue, that's theta 1. DQ, theta, NQ, theta, and DQ, theta 1. So another possibility is to implement a priority queue with 5 queues. So you have Q1, Q2, Q3, Q4, Q5. Q5 is the most important queue, followed by 4, 3, 2, 1. So when an element of priority 3 comes in, it goes into 3Q. When 2 comes in, it goes into 2Q. When 5 comes in, it goes to 5Q. So imagine these queues are all loaded up. So the process of dequeuing is going to be theta of the number of priorities. Because you have to check in the worst case. Do we have a 5? No. Do we have a 4? No. Do we have a 3? Okay. Take that. Get the idea how that works? So that's an implementation of a priority queue using multiple queues. So what's the complexity of that? Well, the complexity of insertion is what? I guess we can call it theta 1. But the dequeuing basically becomes theta of the number of priorities. So if we have, for example, 100 priorities, we might have to do 100 checks to see which queue is available. Which highest priority queue is an available client. Most of the time, priority queues are actually implemented using heaps. And here's how they work. So imagine that we're going to have a priority queue implemented as a max heap, where the priorities are 5 is top and then 4, 3, 2, 1. But again, we could have many more priorities. We could have 100 priorities, 1,000 priorities. It could, but we'll keep it as 5 for now. So what's going to happen is the element at the root of the heap will be coming out next for service. So we have a heap, we have a max heap. The first element coming out is going to be this one. So how are we going to handle that in terms of complexity? Before I say anything about that, let's think about we have already a priority queue with lots of elements in it. A new element comes in. What's the complexity of queuing that element into the priority queue? Well, in this case, notice that we have the invariant of the max heap invariant was that the root or a parent is greater than either child. Well, we can't have that invariant if we're going to have a priority queue. Why not? Because we're going to have multiple cases of the same key, the same priority. So our invariant has to change to what? Greater than or equal to? Greater than or equal to. So our greater than invariant becomes greater than or equal to invariant. It still means that in the root of the max heap, with that invariant, will be the maximum priority element. But there could be many other maximum priority elements. In fact, if there are 50 max priority elements in the heap, then we know that the children of the root are also going to be top priority. Get the idea, right? Okay, so what's the cost of queuing a new element into a heap? Well, again, the worst case is going to be, I suppose log n will be the, but if you think about it, it's really not even log n, because there's zero probability that if we have a priority 5 element, that this priority element is going to kick it off. It's not going to kick it out. Why not? Because even if you compare 5 against a 5, it's fine. Leave the 5 on the bottom. You're not going to switch a 5 with a 5 because it's part of the invariant. See what I'm saying? So, in fact, what's the priority? What's the likelihood that, let's look at it this way. Let's say we have 5 priorities. And for the sake of argument, we're going to say that we have 1 million elements. Okay? And for the sake of argument, we'll assume that the number of priorities is approximately equal. So what percentage of the priorities are 1, 2, 3, 4, 5? 20%. Because we're going to have 20% 1, 20% 2s, 3s, 4s, and 5s. Okay. So my question to you is, what is our expectation with 1 million entries in the priority queue? What is our expectation of the priority levels of the elements at the bottom level? Well, the question can be rephrased as saying, what percentage of the nodes are at the leaf level? This is an easy question. This is the easy question. What percentage of the nodes are at the leaf level? Is it 50%? And if we're talking about a full tree, why? Because it's a binary tree and it's full, and it doubles. So we have 50% are at the bottom level. So, what percentage are priority 1 in our example? 20%. How about priority 2? 40%. How about priority 3? 20%. Okay, what percent are at the bottom level again? Would you expect that all of the lowest priority are going to be at the bottom level? Does it have to be true? No. Is it going to tend to be very strongly true? Yes. So we can expect all the bottom priorities, priority number 1, to be at the bottom level. How about priority 2? Are you going to expect most of them, if not all of them, to be at the bottom level? Yes. Yep. What about the rest of level, the bottom level? We're going to have about half the 3s, roughly. Now, why is this roughly? It's roughly because the heap is not exactly, you saw there could be differences. You could have much lower values here and a little bit higher values here. Okay? But when you talk about only 5 different values, they're going to tend to align along the percentages where they're supposed to be. Which tells me the following. Listen very carefully. If you look at this tree, which is 1 million elements, 500,000 of them are on the bottom. And out of the ones that are not on the bottom, which means they are on all the levels minus 1, it's going to be priority 4, priority 5, and half of priority 3. Am I right? What percentage is that? 50%. So 50% of the elements are going to be in the top, let's just say, 19 levels. You know what I'm saying? Why I'm saying 19? Because log base 2 of 1 million is approximately 20. So I'm just kind of equivocating here. So I'm just kind of saying, so the bottom level is going to have 500,000 elements. The other 500,000 are going to be comprised of half of the priority 3 and all the 4s and the 5s. What is the probability that a new element coming in has this priority 1? I gave you those odds. Equally likely. So what's the probability that a new element has a priority 1? 20%. What will be the complexity of adding that to the heap? 801. Because one comparison, you're good to go. Wherever you go, you're good to go. What will be the probability? What will be the complexity of a priority 2? What will be the probability of a priority 2 element? 20%. Okay, now what is the complexity of adding that element? Well, if it goes under a 3, done. If it goes under a 2, done.